Okay, welcome to the fourth meeting of the seminar. We are now live again. And today the topic is Russian constructive analysis and constructive recursive mathematics. And first I want to hear if you have any questions before we get started about the reading or anything else. So the first order on the agenda is I asked you to read the short paper by Kushner on Markov's analysis. It's kind of an overview paper, and it's not difficult at all, so there's no reason to close read it like we had to do with the Brouwer stuff, but we had to really focus on every sentence. I tried to see if I could find some good stuff from Markov or Shannon, but they appear to have been very focused on, when they were writing mathematics, it would be theorem, proof, definition once in a while, and that's about it. So let's start the way I did the other times by putting up a little timeline related to what we're talking about, and then we'll talk about Kushner's, some of the points in Kushner's paper, and then we'll talk about the chapter in Beeson on the results from recursive analysis, basically. That'll involve a lot of recursion theory. So last time, the other time we had when Brouwer was born, 1881, and so now we're doing the Russian constructivism. So let's see when Markov was born. He was born much later, 1903. Markov born St. Petersburg in Russia, not in Florida. And then, of course, we only get the formalization of constructive logic in the 30s, starting with Heiting's dissertation. And then we talk about all of Brouwer's mathematics basically happened before the invention of the Turing machine and formalization of algorithms in terms of recursive functions, partial recursive functions, and all that. Let's just recall that that mainly happens in 1936. So you have papers by Turing in which he also uses the Turing machine to define constructive real numbers, basically the same way as Markov would use them. And we have Gödel and Church. So that happens in 36. And then basically we have to go to 1947 before Markov starts getting interested in or set himself on the stage on recursive mathematics and constructive mathematics. So in 47 he has an important paper in which he proves that that the word problem for semigroups is undecidable. So let's situate that in time. Semigroup word problem. Yes. Undecidable. And I guess we could put in here, I originally thought we would talk today about cleaning realizability as well, but cleaning realizability is 45. And then in the following years, so basically between this time and 1950, Markov starts a school in the sense that he has many students who are interested in developing recursive analysis on the basis of his notion of algorithms, which he calls Markov algorithms, or we call Markov algorithms, sorry. Markov starts school on constructive recursive analysis. And let's see, what else did I put here? His book is published in 1954. Markov's theory of algorithms. And they do a lot of work in this period. We'll see some of it mentioned in Kushner's piece. Just one more undecidable problem that I want to mention here is 1960, in which Markov proves that the classification problem of four-dimensional manifolds is undecidable. Yeah, and then let's put one more thing. 62. One of the high points of Russian constructivism is Shannon's book on functional analysis. Okay, and I don't know if you noticed it on the web page. I put under additional resources the hymn to constructivists that was composed in this period by one of the Shannon students. Let me see. I just want to read a little bit from it. I think it's very amusing if you haven't looked at it before. Let's see. I imagine the streaming is going to be quite slow because my web page is not loading very fast. Let's see how it goes. Okay, so the hymn of the constructivists, composed about 62-63 by Sergei Maslov, and here's a translation. Though we are few, but we are constructivists and full of ardor and fervor, not scared of heckles, we advance the science of tomorrow. Algorithms will solve all our problems, prove theorems, corollaries, and lemmas. Algorithms will answer all our questions, except where there are no algorithms. So that encapsulates quite nicely the spirit of Russian constructivism. You reduce everything to algorithmic things and things you can formulate with respect to algorithms, and when there are no algorithms, they're silent about the matter. It's not an issue. So I encourage you can read the other verses in the break or later. It's on the course website. Okay, so now to Kushner's piece. So here are some things that I made note of. In section 2, there's also a statement of what Markov's school takes to be constructive mathematics. We study constructive processes formalized in terms of algorithms, and you only recognize potential infinity and things that are can be generated by an algorithmic process, but no completed infinity is accepted. And then they note that you have to change the logic, ensure that whenever you claim something exists, you can algorithmically produce it, or when you claim that you have a disjunction, then you can algorithmically decide which way or the other. Okay. So that section concisely states what they're about. And let's see. Section 4 gives us their version of the continuum, the notion of constructive real numbers, which are taken to be pairs of a rational computable Cauchy sequence together with a functional that gives the modulus of convergence. But they also, this is interesting, so this is written a bit later, but after the 60s, it was realized that it's not quite enough to just look at the computable reals in this sense. You also want some time to state some results about relative computability. So they introduced these. So here it's called the D1, and later you see the DNs. And these are the reals which are computable with respect to an oracle for the jump or some iterated jump of the halting set, right? So this is already a departure from the strict only absolutely computable things, but they found it convenient to also phrase things in terms of relative computability. And when we look in Beeson, we'll see some examples of why you would want to do that. But there are also some examples mentioned here that make that clear why you would do that. So he calls the elements of D1 the pseudonumbers. Okay. Then I think maybe it's worth noting in section 7 some of the results in point set topology. For instance, the counterexample to kind of a strong counterexample to the intermediate value theorem. You can have two recursive paths in the unit square. One path, each path connects opposite corners, but there's no point in the intersection of the two paths. Okay. And then I just want to mention the final section, section 12. So he's at this point he says the revolutionary claims are perhaps behind us, but he thinks constructive mathematics has its worthy place among other mathematical trends. What can be developed, the very development of mathematics on a constructive basis can be regarded as a bold and valuable experiment, whether or not we agree to consider constructive mathematics as the only one. Okay. Again, another perhaps softening of the program. In the hymn there, that was composed 20 years earlier, it ends with every first-year student will eventually realize that constructive mathematics is the true way, and so on. So the claims have been softened a bit.
What I do find interesting is that he asked the question in section 2: is it realizable the initial revolutionary intention of rebuilding mathematics, not just building mathematics, but rebuilding, and recapturing what we already know in some sense. And then throughout the rest of the article, it's like, it's not the same, we're not recapturing the same things. And at the very end, it's like, well, maybe it's just one other type of thing to do.
Yeah.
That is interesting.
It's interesting. Yeah. It's one of the few talking documents I could find from the school. As I said, the translated works by Markov and Shannon are all to the point and don't really dwell on philosophy at all. Okay. So maybe one more thing. In the very last sentence, in particular, the purely syntactic nature of the mathematical universe is, in the opinion of the author, of exceptional interest. So that's, I guess, that re-emphasizes the point of view that they have in this school, that syntax is everything. But quite opposite to what we saw Brouwer talking about, where syntax was something flawed and accidental, and what really matters was the mental construction. Okay, so completely opposite point of view, but many similar developments, but also some differences. Okay, so what we'll do for the rest now is we'll talk about the results in Beeson's chapter 4, and then we'll at points try to compare to how things are for Brouwer's analysis. Okay. So section 1 is about constructive recursion theory, and let's just hear from you guys. How many have not taken a course in recursion theory or computability theory?
That's a very basic introduction.
Hmm?
Besides a very basic introduction.
Yeah.
Only the very basic introduction.
Okay. So some of the arguments are going to be a little difficult to follow if you haven't seen it before. Otherwise, it's just recursion theory. And a lot of the arguments in this chapter are just recursion theory. But if it's the first time you see them, it might be a little, oh, how exactly does this work? So we'll try to spell out some of the details. So yeah, so let's put on the board some of the notions that we'll need. So I suppose you should know what is a recursive set. Natural numbers, one for which the characteristic function is total and recursive. And you should know what an RE set is and what Pfenning calls a semi-computable set. So an RE set is so the range of a computable function, or there's many different characterizations, and he takes a semi-computable set to be the empty set or the range of a computable set. And we'll only need a couple of results. We'll need to know that some semi-computable sets are not recursive. For instance, the halting set or the standard set, named the set of indices for an algorithm where when applied to its own index, it halts. Right? So it's a particular case of the halting set. It's interreducible between the halting set. And then we need to know the reduction theorem. So if you have two RE sets, A and B, then you can find disjoint subsets, maybe like this. Prime, B prime, A prime, and B prime disjoint. Does anyone know how to construct those? If you have the indices that generate A and B, how do you generate two new indices that index disjoint semi-computable sets?
A prime and B prime have to do also.
Oh yeah, that.
Yeah.
Okay. Find A prime, B prime, A prime, A. That is still a requirement, right? Certainly. B prime,
Otherwise,
B.
it's just
Yeah. A prime union B prime equals, of course, like this. Okay. So how do we do it?
And disjoint.
And disjoint. A prime. Thank you. Any idea? Okay, so we could just start enumerating, dovetailing all the possible outputs from A and B and order them, and make sure you would plop something in A prime if it comes into A first and has not been added to B before that, because we can order things this way and then we can do it the other ways. And then anything that's eventually in either A or B will come out in either A prime or B prime. So that's why we get this part. And because we make sure that we only add it when it hasn't been added before, then we get this disjoint. So that's a sketch of an argument. We'll refer to a recursion theory text for precise details. But the point of the reduction theorem is that now we can do this uniformly in the indices for A and B. So we can enumerate all disjoint sets of our semi-computable sets. Okay. And now the next thing we need, that was the reduction theorem. Then we also need the existence of recursively inseparable semi-computable sets. So recursively inseparable semi-computable sets. They will be RE because if one of them is finite and it's an easy thing. So it would be two infinite RE sets, A and B, but no X is recursive with X included in, let's see what I want to say, picture, so disjoint, so here's A, here's B, and we want to know whether there's a recursive set X, so that A is included in X. No recursive X, such that A is included in X, and B is disjoint X. Okay, and we can again use this diagonalization trick to do this, to get such a to get this A and B, because you can take using the reduction theorem. Okay, so let's do it in detail just to make sure we see it. So suppose A and B and runs through all disjoint semi-computable sets. So we have these sequences, and as we run through, we get all the disjoint sets. We can do that using the reduction theorem because we can enumerate all possibly non-disjoint sets, and then we apply the uniform reduction theorem to make sure we run through only disjoint sets. Okay, now we define, I need my sets A and B, so I just take A to be the ends, which n is in Bn at An, and at B, likewise the end, which n is in Bn. Now they are disjoint because if n is in both An and Bn, well, that then be absurdity, because An and Bn are disjoint. And suppose you have a recursive X, then both the X and its complement are recursively enumerable, and then you get a contradiction. Okay, so that's a construction. So I think that's enough background to read the rest of the chapter. Let's now have a look at 4.2. The main thing here, I guess, is the results on the order relations on the recursive reals. So you can refute this weak disjunction that either that for all x, either x is less than or equal to 0, or greater than or equal to 0. And if you have, if you assume Church's thesis, or in other words, if you are working in the Russian constructive universe, the recursive reals. Okay. And That's again using recursively inseparable RE sets. I don't think I will dwell on the exact thing, but the main theorem, I think, one of the really important theorems is in the next section, section 3, which is attributed both to Kreisel-Lacombe-Shoenfield and also to Jaden independently. And that's from 1959. So what this says is that if you assume Markov's principle, and this is something that Markov school did, they assumed Markov's principle, then every effective operation type 2, so every functional that takes indices for total recursive functions and is extensional with respect to those, every such index is continuous pointwise everywhere. Okay. So there's a lemma that if you have a modulus, an almost modulus of continuity, then that suffices by comparing things with the inputs that are canonical functions extending sequences. So you have a finite, so there's a natural topology on bare space that functions from n to n, and you can canonically extend a finite function with zeros everywhere else. And just by comparing a functional on those kinds of indices that canonically code for such sequences, you can, if it's extensional, then if you have a modulus that works with those, then it works everywhere else. That's kind of the easy part. So we've reduced it to this part. So we want to show that Markov's principle implies for every element of E2, E2 is, as we just said, an effective operation on elements of E1 that respects extensional equality. Then there's an almost modulus of continuity. And it's a quite delicate thing. So let's write out the definition. And you need certainly some appeals to the recursion theorem to justify it. So call this the KLS theorem. Markov's principle implies all the E2 and all y E1 that exist in such that for all, let's see, W in E1, if, and then there's a bit of notation, if the function denoted by so if y and w agree up to n. So remember, this is Beeson's notation for the list of the first n values of the function indexed by y. This list is equal to the first n values of the function indexed by w. Then z y is z y to w. Okay. And then the lemma is that it's enough to show instead of all w here, you could take all t of length n, I suppose, all t sequence instead of sequence, I suppose, and then t $ is the the canonical index for the function that has this sequence as its first values and extend it by zeros. Okay, so this is the variant that we're actually showing. Okay, so the proof, it's kind of short in Beeson, although it's a lot that goes into it. So I don't know if did you find it easy to understand? Did you check it?
Read through it.
You read through it?
Yeah.
How was it? Okay, so definitely something to talk about. Okay, so what we want is we want a realizer for this quantifier combination, first of all. So we want a recursive function in two variables that gets us the n. That's the almost modulus of continuity. Okay? And we want to define n is equal to m of cy, and we define it to be using a search at least j, such that j is a computation for e on itself. Okay, so where I still have to give you this index e to be determined. Okay. Now, and to help us define e, I still have uniformly in c and y, and now an extra index v. So for all v, we use the recursion theorem overall to define an index pv, which on input x does the following. It outputs the value of y at x if phi v, so this v applied to itself, v, does not converge to 0 in less than or equal to n. And it's a little unclear in the text. I think it has to be in that we're using the recursion theorem overall to refer back to this thing we're in the process of defining. So we have to check that this is well defined in the end. So this is the m of cy that we're defining. And it is phi on this canonical sequence function applied to x if t, so to tell you the sequence number, if t is the least sequence number extending this sequence of function values y, where we take the least n such that phi v applied to v converges to 0 in n steps. Okay. So suppose we're not in the first case because it did converge to 0 in less than n steps. Then you take the first time, the actual number of steps, use that many number of steps to tell you how long a prefix of the function y you are required to find a sequence number extending. But then there's a further demand. You have to keep searching, because not only do you have to have the base sequence, but you have to search for all possible extensions which satisfy the extra condition such that where is it? The E2 functional we're considering applied to $t is different from phi c on our input at which we're checking continuity. And it might be that we never find such a thing, which is actually a good thing, right? We want to show that that we have this modulus of continuity. So any sequence that is so this long should give the same output as phi c of y. But we now we're writing a partial recursive function that keeps searching for a counterexample. So you can kind of see how we might end up needing Markov's principle, because if we fail to find a counterexample, then we might be okay, and then it's undefined otherwise. I still haven't told you what E is. This is just a helper function in the overall appeal to the recursion theorem. Now, E itself.
What are you referring to when you say the recursion theorem?
I'm referring to the fact that if you can define a partial recursive function which appeals to as a parameter to an index, then you can find an index for which it's equal to where you apply that index for the parameter.
Oh, yeah.
Yeah. Okay. So a program is allowed to use its own code as a parameter. So now the E itself, which is the critical component in our modulus, or almost modulus, phi E applied to any V, which V is the equal one of these, is now simply 0, which is the good case. That is, if phi Z of PV equals phi Z of Y, and one if Z of PV is different, and I guess at this point it could possibly be undefined. We only know that the computation indexed by Z terminates if given a total function, but a priori the PV might be partial. So this might still not halt, in which case this just doesn't halt either.
If there's no such T dollar.
Yeah, for instance, if PV is not total, then we don't know what phi Z of PV, we don't know that halts. We don't know that phi Z halts on every total input. So now the first thing we want to show is that, in fact, phi E of E is always 0. And this is by an appeal to Markov's principle, right? So suppose the assumption that phi E applied to E halts and converted to 0 leads to an absurdity, right? So that's the thing we do. Then we can check that P sub E is extensionally equal to Y.
The first class of 5P.
That's right. Because we assumed it would never convert to 0, then we have the first clause of the definition of P sub E. Okay? And then P sub E and Y are extensionally equal. And hence, when we feed them into the C functional, then we get the same output. So then we look at the definition of E. Okay, so if phi Z of P E equals phi Z of Y, then phi E of E is 0, but that's it does converge to 0, but that's what we assumed it didn't. So we have not phi E sub E converges to 0. Hence, phi E sub E converges to 0. And then the rest of the argument is we have to check that.
Can you explain really quick why phi Z of PE is equal to phi Z of Y?
That's because we assumed from the get-go that Z was in E2. That is, it has the property that if you feed in extensionally equal indices, then you get the same output.
Oh, and why is DV acceptable?
Yeah. Yeah. Okay, so now we have to check that n, as we defined it there, is an almost modulus. So you just take any sequence that extends the first n values of y. Right, so you have the function y, you take its first n values where n is m of zy, where m of zy is the number of steps to compute phi e of e. And okay, you now know that phi c of such a sequence, it does converge, right? All these sequences are total functional, so you can just compare with the result of phi c of y. We want it to be equal to phi c of y. If it's equal to phi c of y, we're all good. That's what we want to show. If it's not equal to phi c of y, we have to derive a contradiction. But in the case that phi c of s dollar is not equal to phi z of y, then using the second clause, we will find such a sequence number. So phi pe of x is equal to phi, I guess, phi t of s, phi t dollar of x for all x, and where you take the t to be the least one. That's this counterexample. We want to, so suppose there's a counterexample, then there's a least counterexample, and then for this counterexample t, the t dollar is extensionally equal to p sub e. But then if they're extensionally equal, you get the same output when you feed them to the functional. And then that contradicts this. Then you would get output 1 instead of then you get output 0 after all at phi e applied to e, and that's a contradiction. You get both output 1 and output 0. Okay, so it's kind of a convoluted thing. And if you want to really double check that this is an allowable recursion, I will link afterwards to Jaap van Osten. He has a good set of notes in recursion theory where he really spells out in detail why this is an allowable definition. I think Beeson plays a little fast, and it kind of assumes that you're well-versed in recursion theory. And if you don't, you might be a little unsure, oh, does this really define a well-defined index?
Especially the second clause of PV.
Yeah.
That particular counterexample is.
Yeah, and also because you're appealing to m of cy, right? That's the n. And you're appealing to that at the very moment you're trying. So, but it can be done. So I'll link to another source where there's a very spelled out proof. But we have Beeson available, so that's also good. Okay.
A quick question. Like many in the Christian religious, is there a heuristic argument for why Markow's principle is useful?
Well,
aside from that, it's really useful.
Yeah.
So it is just a double negation relation, which we're not supposed to have. Right?
Yes, but on the other hand, you're supposed to say, okay, what am I supposed to do when I want to prove? So how would you argue in recursion, constructive recursive mathematics? I want to prove that there exists an n such that something decidable, right? And I have as an assumption not the existence of such a thing. And then what does it mean to give an n? Well, it means to give an algorithm that computes it. And there's an obvious algorithm that, namely the one that searches. So the step is whether you take as evidence this not a value as valid evidence that this search will stop. Certainly there is an algorithm. The question is whether it's acceptable to you that it halts when you have proven that it can't not. And then it's a philosophical matter. We can dwell on this a little bit.
Maybe there's a question of, my concern is if you were trying to set up a nice, safe, constructed universe, this would maybe give you too much. This would give you a longer speed of for future things. It would just collapse back down to the possibility of this.
Well, we know that it does not collapse, right? There are results later in Beeson. We already saw a particular counterexample based on ordering some reals. We saw a similar one from Brouwer's, where we also had using the continuity principles, we got the negation of an instance of log excluded middle. And the same thing you can get from Church's thesis and Markov's principle. Of course, Markov's principle alone would not give you that. But if you have Church's thesis and Markov's principle, you do get that, right? And we'll talk later about models for, say, the finite types. Actually, we'll start talking about it in a little bit. I don't think we can separate every principle at the moment, but eventually it's something that you could look into. For all these non-classical, possibly classical principles, can you find a model that has one be true and the other is not true in the model? And so on the meta-mathematical side, we can say a lot about whether Markov's principle gives you too many instances of excluded middle, and typically it does not. Okay, but let's come back to the philosophical point. What do you think of this argument that if a search can't not stop, then it stops?
What kind of evidence could you bring to bear on that kind of conclusion? In either direction.
Yeah.
Like computation.
Yeah.
You have the algorithm. You know it can't not halt. Why would you, or why wouldn't you take that as evidence that it halts?
Construction.
Well, Brouwer couldn't really have this. It seems that before you have really formalized the notion of algorithm, it might very well seem that you should not accept something like this, because the notion of rule or algorithm is a bit vague, and you only take as something to be a rule if you have a mental picture of it, which is a different notion of rule than the one we get from Turing and Markov and Church. Certainly you can have that, but I think we can try to look up Göran Sundholm, who's written about this. He would say that he is an intuitionist who thinks, I hope I'm not putting this the wrong way, but he's still alive, so he can speak for himself, right? I think he would say that for him, he would not accept even the informal Church's thesis. So the Church-Turing thesis is something like this. If something is humanly computable or mentally computable, then there is an index of a recursive function that performs that computation. And what kind of evidence would you have for that if you're an intuitionist? So classically, it might seem clear that you have that kind of, that you can make that jump if you do the kind of informal rigorous analysis. I don't know if you have ever looked at Kreisel's work on this. But if you're already an intuitionist, it seems that there's an extra leap required to show that something would have an index, which namely you want to have the you need the mental construction that process terminates, and that's exactly what you don't have. You have the mental construction of the process itself, but you don't necessarily have the mental construction that it terminates. That would be an extra reflection step. So you can see why maybe from an intuitionistic standpoint you could not accept the Church-Turing thesis, and then you certainly would not accept something like the Church's thesis in Russian constructivism, and you would reject Markov's principle. On the other hand, if you do find the informal church's thesis compelling, maybe you would find Markov's principle more compelling. What do you think of that line of analysis?
Outside of you're not sharing anything with it. Still understanding
You think that's the first direction we just prove so that if we decide to reject church's thesis, we'll get some more it's not a traceable relationship. But you said it just.
Yeah, I hadn't prepared this line of thought, so I hope I can clarify it a bit. Which direction were you asking about again?
The first one. So if you reject the church's thesis or there's then you have to reject Markov's principle as well.
Yeah, let's be very careful here. We're not saying we reject the church's theorem, but we do not accept. That's the difference.
Okay.
Do you see the difference?
No.
No? So to reject... to reject it would be something like, I believe I can construct a...
Reduce it to absurdity.
Yeah. Whereas, yeah, you could reduce it to absurdity. So, whereas not accepting it would just be, okay, I don't see the evidence for it, or I don't... okay. And then there are two parts to that. One was an analysis of what the evidence of the informal church's thesis would amount to. And maybe you could, you agree with that,
yeah.
But not the connection to Markov's principle. And that, okay, so let me first make clear that if I said something about Jørgen Sundholm, that would be the first part of that, not having sufficient evidence for the informal church's thesis. And okay, and then I imagine that I saw a connection to Markov's principle. And the connection would be something like, so I have maybe I have an informal, well, no, I do have yeah, maybe you're right. So in Markov's principle, say primitive recursive Markov principle in particular, you have an index for a search. And you have the evidence, which is now perhaps a mental construction, that this search cannot not stop. Hope I have the right number of negations. So if you want now to have a, or maybe I was thinking about the other direction of, it's kind of the converse of the informal church's thesis, that if something is computable by a Turing machine, then we have a mental construction that emulates that. Everything that's computable by a Turing machine, we have a mental construction that emulates, and that's where it fails, right? Because the bare fact that a computation cannot fail to stop does not give me mental evidence that I can really perform that computation myself. So it's actually the other direction that's usually taken for granted, that it's that a skepticism about Markov's principle seems to be related to.
Okay, so we can do the next one. If you want to describe the Markov's principle, which is that I have no construction, given the fact that I know that it's not possible for this search to not stop, then it seems like I should also have evidence that if a particular function is recursive, then I should have no.
Yeah.
So explain that.
Yeah, that's
okay.
yeah. Okay, so different models first. Good, but yeah. Okay. Yeah, it's a little hairy. Okay. All right. So let's go to the second part of this section, which is about. So Beeson calls it Tseytin's theorem. I think both this is kind of an extension of the Kreisel-Lacombe-Shoenfield theorem. So you could put all names to both these statements. So this is again 59. And I think today you always have this problem with Cyrillic. How do you transliterate it, and how did they transliterate it in the past? So let me just see what I've seen. And I don't remember the standard, but which standards which correspond to. But there was an American standard, and there's an ISO standard, there's a European standard. There's a standard that Russians use when they wanted Roman transliterations in their passports, and that's often what currently living Russians would use, because that's what they show at immigration, right? So, okay, so either Tseytin or Tseytin. This is often what you see in mathematical writing from the time of Easton's book, but you also see many variations, of course. But the point is, if you have so if X is a complete separable metric space, and if Y is any separable metric space, then Markov's principle implies that any function which is tracked by an index, of course, which is understood here in this setting, is pointwise continuous. And in Wiesen, the proof for Kreisel-Lacombe-Shoenfield is repeated but dressed up to give this statement. In the particular case of Baire space itself, so to say functions from Baire space to Baire space, you can recover this part from the KLS theorem just by looking at the arguments and the individual ends values of the sequence that approximates the output. So I think what's more interesting than trying to redo the proof, which is very similar to the proof of the KLS theorem, is just to recount how we treat metric spaces, separable metric spaces in recursive mathematics. So we represent X as a subset of Baire space, but with a different topology or different metric. So it's all those elements of Baire space. This is Wiesen's definition, where rho is a metric on n, and then you define the metric on X to be the limit X and Y. Okay. And I think this is not in this particular part, but just want to, this chapter, I do want to mention that for us in recursive mathematics, we take a compact metric space to be a compact separable metric space to be a complete and totally bounded metric space. Where totally bounded means that you, for every epsilon, or rational epsilon, you can construct a finite list such that for every element you can construct which of those finitely many is less than epsilon away from. All right. Okay. And I do also want to mention that, highlight the fact that Wiesen mentioned that this was independently derived by Joan Moskovakis in '64, before this was available in the West by Jaden. So this is a point of analogy with Bravarian mathematics, right? We saw last time that for Brouwer, it was also the case that continuous function on metric spaces, any function between metric spaces was continuous. So we get a similar result here, but then we'll soon see a lot of dissimilarities. Okay. Then it's curious that in section 3.2, the the hereditarily extensional operations are introduced. And okay, maybe same. We have the honor of being visited by Mark Besem for the next 3 months, and he's done some very important work on these models of functionals of finite type. So he will maybe say something about that and Bravarian principles later on in the course. I hope to convince him. Okay. But Besem doesn't use the structures right now. He just introduces them. Then let's look in section 3.3 that, okay, so now we know that there are these moduli of continuity, but I think it's important to mention this lemma that there is no extensional modulus of continuity. The modulus of continuity is a very intentional thing. You can kind of imagine that. So let's skip the proof. But let's look at exercise number 1. So this is another point of connection to Bravarian analysis. Here, we said a variant of the KLS theorem is that every effective operation from bare space to the naturals has a recursive neighborhood function that works on what you would have as inputs, namely the recursive functions. So we saw that the bar theorem could be construed as a way of saying that if you have a Bravarian function from bare space to the numbers, then you have a neighborhood function in Brouwer's sense. So this is another point of analogy between the two setups. But soon we'll get to some dissimilarities. Namely, okay, section 4. Let's see how time is it. Maybe we'll take a break and then we'll do Specker sequences. So let's take a 5-minute break.
There we go. Have you seen the new book by Bonn?
No, I'm not.
Yes, I think you would click at least to glance through browser.
Yeah.
Would be I've sent you a.
Do you have a? Yeah.
Yeah. So it's for the higher order.
Yeah.
So you select HEO.
Yeah.
This one is
Yeah. Oh, very good.
Yeah. Well, it's together with Longley.
I know that Longley, yes, he had a series of notes lying on his webpage for a long time. I don't know if they were ever published. But
Yes, but now this is volume.
Okay, yeah. Yeah, because I've seen the notes by Longley on. They were good.
We made it.
Yeah.
I've been trying to get
Yes,
the work on
rather
it.
they made
Yeah.
I submitted it.
Yeah.
I sent you that thing.
Okay.
We'll go with it.
Yeah, therefore,
Are people taking it?
I'm taking my own.
Is there, could I Still in orders.
There's
Maybe they do.
maybe you can ask.
Just wait.
Yeah, is there a cafeteria in this in Dorothy? There's not, right?
No.
There's a vending machine. That's about it.
There's a cafe that's really accessible for you to go over to the.
Yeah, if you go to
Yeah, but I would just.
Yeah, I think you would let you. You have to change buildings at separate floors 3 times.
Right.
Yeah.
Or 7.
That's it, take this out.
Do you know what Chayton's first name was?
No.
Because there's
Because I
a,
think it's not.
yeah, I'm trying to find him.
Initials GS.
All right, I found a GD Chayton, but I guess it's the wrong one.
So they're an American.
One of them gave a linear translation or a linear translation of propositional formulas to actually satisfiable set of clauses. Yeah. When you use an auxiliary variation in the formula in parse tree, you put auxiliary variables that we know in the parse tree. But I think that's not its own special.
Yeah.
There are more in math Maybe at least 3.
Yes.
I'm trying to find the original Cyrillic spell. That's the search.
That is here.
I don't think it was referred to there. And I also checked out, by the way, if you're interested, I'll return this to the library. And in English, this is the best resource for constructive recursive mathematics. That is Kushner's lecture notes. But there, it's also everything is transliterated. There's no Cyrillic originals, but it does say GS Jaden. But you could look up if you could find.
Was born in 36 in St. Petersburg. That'd be the right one.
It might be, but you could look up the proceedings of the International Congress of Mathematics in Moscow, '66. You can probably find the table of contents in Russian, and that would allow you. He has 2 papers there, so then you would be able to find the
Initials in Russian.
yeah, maybe
Yeah,
find
so
some
it's-
information. And of course, if you find something, you could start a Wikipedia page for him. That would be great. Then other people would be spared trying to agonize over finding him. Okay. So now Specker sequences. So that's section 4. And we'll just do the weak part, which is step is sequence. So there exists Rn, I guess, weakly increasing bounded sequence of rationals with no limit. Right? So of course, classically, every bounded increasing sequence of rationals has a least of a bound, which is its limit. And there are 2 variations of this theorem, and the one I give here is in this negative formulation. So you assume it has a limit and you derive a contradiction. There's also a stronger version where you give a sequence, and for every real, you give a rational that is such that it's eventually bounded more than that epsilon away from the sequence. So it's really strongly doesn't converge. But I'm just going to give you the weak version here. Okay. So fix proof. Fix F into M. Injective. Total recursive. Such that the range of the image of F is not recursive. Okay?
Can you give an intuitive justification for why there exists such?
Yeah, in fact, every infinite recursively enumerable set appears as such a range. Why? Okay, suppose you have an infinite recursively enumerable set. Then you start dovetailing to generate elements of it, and you keep a table of which one you found so far. And you output as on index n. So on f of 0, you start this search that searches for all possible ways you could get a number in your recursively enumerable set, and you output the first one you get, and then you make a list of it. Okay, then f of 1, you do the same thing, but you output the first one that's not f of 0. Then for f of 2, you output the first one that's not f of 0 or f of 1, and so on. So you output at each n, you output the first one in your set that's not been outputted before. And classically, or with Markov principle, of course, that you have an infinite, depends on what you mean by infinite set. If you have you really have a way of making sure you always get a new one, then it's clear this is total, because for every n you've only enumerated finitely many so far, so you're bound to find a new one. Okay, so that's how we get such an f, and then we define R sub n Yeah, so you could take the image to be the halting set or something like that, and just start enumerating sets. I think if you want this strong Specker sequence, you probably need to start with a particular one, maybe the halting set, take a complete RE set, and not just any non-recursive RE set. But we don't need that strong conclusion right here. You can take any one. And then we define Rn to be this thing, 0 to m to the minus 1 minus. Okay? And so one way to think about this, so these are bounded by so every time you have at least is that the right thing?
Yeah, it's bounded by 1.
It's bounded by 1, I guess.
Yeah, it's bounded by 1 because you're going to eventually get
Because of the agent.
yeah, because of the injectivity, it's bounded by 1. Okay, I guess strictly, but not really needed. Okay.
And we mean this in your constructive sense.
Yes. If I think yeah, you could give it that sense. So let's do that. This is clearly non-decreasing, and it's bounded by 1 because of the injectivity. And then we assume for contradiction that it converges to a recursive real. So that's what we would be aiming for, this negative conclusion that it doesn't converge to any recursive real, rather than the strong version, which would be for every recursive real, there is a bound so that eventually it stays away from that real by that bound. Okay. And the proof is that not hard from this point. We just want to derive a contradiction. We check that we check that it's recursively Cauchy, and we look at this relation P of m comma k. So P of mk is defined by the distance from, we assume that x converges to, the Rn's converge to a recursive real x. So it's defined by the distance from x to rk is less than 2 to the minus m minus 1. And this, of course, is Re. So we take a selection operator in MD such that for every m you give such a k. You search for the k. Then you use this to get a bound for how far the nth element of the range is. So remember the result that if you have a recursive function that is increasing, and then the range is actually recursive because you can then just check finitely many things, and this is the setup we get here. We get actually a bound for how much you should check, whether you want to check something is in the range or not. But then that's a contradiction to the assumption that we had constructed f such that the range was not recursive. Okay. So what can we get out of Specker sequences? Well, there are some things that are mentioned here. Myhill's theorem. This is one motivation for introducing the pseudo numbers that Kushner was talking about before. There is a uniformly continuous function from R to R, such that if you can solve the halting problem, then f has a uniformly continuous derivative. So the derivative is pseudo-computable, but the derivative at 0 is not computable. Okay, so it has yes, that's an interesting thing. Corollary of the Specker sequences.
Can you explain why that's interesting? Why the halting problem oracles are useful here? I mean, why we talk about that kind of thing in this kind of Russian constructivism? Or is this just kind of orthogonal to that?
No, I don't think it's orthogonal. I'm trying to think about what I thought it was kind of clear from this kind of thing that. So once you start looking at relative computability, you then start seeing many examples like this, where something is you have an index that outputs, say, a constructive Cauchy sequence, but you don't have the modulus of continuity except for solving the halting problem, something like that. And there's another example in the paper by Kushner. Let's see if I can find that. That was a better one, maybe. Or maybe I'm not misremembering. Oh yeah, in section 5, I believe. So on page 55, let us present some relevant results. If a partial recursive operator computing a constructive function that is function from actual reals to actual reals can be extended onto the pseudo-reals, then it's constructively uniformly continuous on a compact interval. There's a function from the reals to the reals which has a continuous extension to the pseudo numbers, and which is effectively non-uniformly continuous on the unit function, the unit interval. And if a function can be continuously extended onto the second pseudo numbers, then it's pseudo-uniformly continuous on the unit segment. So they're trying to grapple with the fact that, in a way, we expect continuous functions on a bounded interval to be uniformly continuous, and we're gonna let maybe defer a little bit because it'll come out right after we talk about the cleaner tree and the failure of the Pfenning theorem in recursive mathematics. That why you want to have these extensions so that look at, oh, well, we have this small discrepancy between what we expect and what we can get by adding an extra pseudo. Is that a start to address it? Yeah. All right. So that's the next note right here. Section 5, the failure of Königs lemma and the singular tree. So remember last time we were talking about Königs lemma and about the Pfenning theorem, right? So here we see an example where this fails rather dramatically in recursive mathematics. So this is the cleanest theorem from 52. There's a primitive recursive binary tree which has no recursive infinite path, but which is infinite. So at every level, there are nodes of the tree at that level. So it's a direct contradiction of the Pfenning theorem, which would say if you have an infinite binary tree, then there are infinite. If there are no infinite, the other way around. If there are no infinite paths, then there is a finite bound on the nodes of the tree. So let's look at the construction. In this proof, we take two recursively inseparable, recursively enumerable sets, like we had in section 1, and Then we define the tree R, and we write it down maybe. Please, singular tree. So if you want the canonical one, you take A to be given by the standard unsolvable set side, the diagonal halting set. But here the way Beeson does it, we start with any two A and B recursively inseparable. RE sets. And then we said a sequence number T is in the tree if and only if it satisfies these conditions. T is a binary sequence. It's binary. So this means all m less than the length of T, Tm. See the 0, 1. And then there are two more conditions. If the length of T number of steps show that J, so for all J less than the length of T, if the length of T number of steps show that J is an A, then it must be the case that T sub J is 0. And same thing, but with if length of T steps show that J is in B, then T sub J is 1. And if length of T steps is insufficient to determine either one, then both are allowed in the tree. Okay. So in the beginning, it looks like the full binary tree. But once you start getting enough steps to compute one of these, it starts getting pruned. Okay. Now, if you have a path, then you can just take all the numbers for which you get 0 in the path to be a recursive separation. So therefore, there's no recursive path. But we actually want something a little bit stronger, but we will get to that. We want not just that there is no path, but we want to show for every f, it eventually leaves the tree. There exists an n such that f of n is out of the tree. Let's see, we also want to check that it really is infinite, that for every n we can find a sequence of length n. So let's see, how does that go? Well, so just make n steps of both for all j from 1 to n, make n steps of a and b, and you can make such a sequence. There only comes a constraint if these n steps put j in either a or b. So for each n, you can make the sequence of length n. You make n steps, and then you just have to check whether you have any constraints on those spots of the sequence. Now, let's have a look at the argument for trying to find for every f which is recursive a stage at which it leaves the tree. Okay. So it's indexed by some index e, and then we see that the sets of inputs for which the output is 1 and the output set of inputs for which the output is 0. This is now a disjoint a pair of recursively enumerable sets. So it occurs in the enumeration of all of these. And this is total. So for every, you try to then apply it to itself, right? We use the diagonal set. If f, which is phi sub e, applied to e is not 0 or 1, then it's already out of this tree because this is a binary tree. Otherwise, you can compute a number of steps that show that e is in a sub e or in b sub e because of we have this enumeration of these sets, and then we get a contradiction. So this is Kleini's singular tree, and now let's have a look at an application, which is the strong failure of the Heine-Borel theorem, compactness theorem. So this is the next section, section 6, about singular coverings. A lot of things you can do with this. It takes a whole chapter in Kushner's lecture notes, but let's just have a taste of what you can do. And you get this theorem by Lacombe, Jaslowski, and Jaden, where you can find a recursive sequence of closed intervals with rational endpoints, all of which are either disjoint or fit together with one endpoint in common, so they fit snug together. And you can then enumerate the open intervals formed by pairs of these adjacent ones where they do fit together, leaving out the middle endpoints, the endpoints, right? Then it's the case that every recursive real belongs to some of these open sets, and the partial sums of the lengths of the closed ones are bounded above by a quarter, and those of the open ones are bounded above by 1/2. In fact, you can get it arbitrarily small, if to be below epsilon and 2 epsilon, say. So classically, of course, it's the case that the recursive reals have measure 0. In this case, we get a strong constructive version of that. We can actually constructively make the measure of the recursive reals arbitrarily small. So let that sink in a little bit. So what do we want from the continuum? We want it to be something full, a full measure, right? And here in constructive recursive mathematics, we can, inside of that system, we can see that it has, it must have arbitrarily small measure. So that's a strong failure of our intuitions about the continuum from within this viewpoint. So I think that's part of the reason why maybe, I don't know whether Brouwer had intuited that something like this would happen if you stuck to law-like rationals or law-like real numbers, and that's why he wanted to have the fuller continuum based on the choice sequences. But it's possible that he had something like this, at least in his intuition, that why the law-like numbers are not as an adequate continuum. Okay, so that's a very interesting result. And the other example, the last one I asked you to read, was that if you have Kleini's singular tree, you get directly functions on compact sets which are unbounded. So at in the basic case, you get now a function on Cantor space. So you search just. So now we know that constructively that if you take the singular tree, then for every element of Cantor space, it eventually leaves the singular tree. So you just have this function defined on Cantor space that says, okay, give me the first time this element of Cantor space leaves the singular tree. Then by the construction of the singular tree, this is an unbounded function on Cantor space. Continuous but unbounded. So in particular, it's not, we don't have uniform continuity on functions on Cantor space. And then, of course, via the usual translation into talking about subsets of Baire space and Cantor space as either compact or complete separable metric spaces, you also get the result from functions from the unit interval to the reals. You can have such ones be continuous but unbounded in recursive mathematics. All right, that's all we had for the reading. Is there anything else we'd like to discuss regarding constructive recursive mathematics, or the relation between recursive mathematics and Bravarian analysis?
I didn't look at the proof, but I thought 8.1 was very interesting theorem.
Yeah, we can have a look at the rest of the section, even though it would be too much to go through all of the proofs, and I haven't studied the proofs. Yeah. So what did you find interesting about 8.1?
It strikes me as being somewhat very counter. It goes against my intuition, perhaps as a classically trained mathematician. That
would you mind just reading, saying what it says in your own words?
That you have a uniformly continuous function where the image is strictly bounded below by 0 and bounded above by 1.
Mm-hmm.
Yet you can get arbitrarily close to 0. So my intuition is that my understanding is that you can't show that the infimum is positive. Is that correct? Correct interpretation? Yes,
that's right. Yeah. Yeah, it's a bounded, uniformly continuous function on the compact interval. It's strictly positive everywhere, yet it's arbitrarily close to 0.
Mm-hmm.
Yeah. It's again a kind of, you can imagine just a stretching around of the continuous function, which is not uniformly continuous. Once you put it between two bounds, then you might be able to get it uniformly continuous, but still not able to have a, yeah, it's a very interesting result.
Isn't that probably showing that in recursive analysis, compactness is not an invariant continuous function?
Yes.
Yeah.
Yeah. So we haven't. So here, Beeson just by fiat says compact means totally bounded and complete. But of course, classically, there are many equivalent formulations of compactness. One of them maybe being that you can that continuous functions attain their extrema. So that's another. I mean, I'd say what are our intuitions about compactness?
So I guess, do you know how the extreme value theorem on the unit? To use the intermediate value theorem, the extreme value theorem.
Oh, first year calculus.
Achieving your infimum unbounded.
Yeah, so when we talk about Bishop's analysis, when I come back from Bonn, we'll see a way how to rescue this by just saying, okay, this is pseudo generality to think about all these kinds of functions. You should really just put in enough restrictions that things are well behaved. That's one way to fix it. Or maybe later we'll talk about synthetic notions of analysis where things are more well behaved again. But definitely something to keep in mind: what goes wrong when you go in these different directions, and how does this interact with our intuitions of the continuum, say, and other things. Okay, let's have a look at the rest of the chapter. The next one, 9, is the theorem of the maximum, revisited. A uniform continuous function which does not attain its maximum. Okay, that's the same as 8.1, right? And then the next thing, let me just read it. There is an effective operation from the unit disk to the complex plane which is real analytic on a neighborhood of each point of the closed disk. It's bounded on the unit circle, but for every bound M, there's a point of the disk where it exceeds an absolute value of that bound. So it's a analytic counterexample to the failure of the maximum principle or boundedness. It's quite bizarre, right? Section 10 is about the topology of the disk, and it has some great stuff. So first of all, in recursive analysis, there's an equivalence between having a unit vector field on the disk of index 1, having a retraction of the disk onto the circle, and a continuous map from the disk to the disk without fixed points. Okay? And so those are equivalent, and what the proof then does is it constructs a unit vector field of index 1, which is something that classically cannot exist. But of course, even classically, it's also in recursive analysis, it's equivalent to, say, defining counterexamples to Brouwer's fixed point and to having a retraction from the disk onto the circle. So you get all of those things. You can actually produce a retraction of the unit disk to the unit circle. So that's another instance of something continuous not being quite continuous or continuum-like.
Section 14 is quite interesting.
Let me go see. I don't remember it.
We have a major problem with this ultras.
What does it say?
In terms of the continuum hypothesis is false.
Ah.
Go into
So
this result there.
You probably you have to pay close attention to what does the continuum hypothesis here mean? What does it mean to quantify over all sets? In this case, do we quantify over recursive sets? That must, I guess, we'll have to read to see the fine print. But yeah, that is good. That's a good thing. A good find. The continuum hypothesis fails. It's proved that it fails. The other extreme one is turn to section 12. You have a subset of the closed unit interval, which is inhabited. You can give a point of it. It's open. It's also closed, but it is not everything. There's also a point you can give outside of it. So in recursive mathematics, intervals are not connected in this sense. Okay.
Like there's a closed subset of the unit interval that's not the whole thing.
Yes. And it's not empty.
Not empty,
yeah. And you can actually give a point both in and out.
These are kind of funny.
Right? So now I think we have a good sense of what can go wrong, or what happens to the continuum and our intuitions of the continuum in recursive mathematics. So we'll talk more about other models of continuity and analysis from a constructive viewpoint, but certainly this is one important strand of it, and it's quite a lot of fun.
So, I mean, I don't want to call them catastrophic failures, but most of all of the ones we've seen so far seem to be in an analysis. Are there any in other branches of interest?
Well, we know that they did a lot of functional analysis, and I don't know, Shannon's book must have been translated. I don't think we have it in our library. But I imagine that there are both things you can recover from functional analysis and things that go spectacularly wrong. Probably outside of analysis and functional analysis, things are more well behaved. Certainly algebra should be fairly well behaved.
It's in algebra, there are a whole bunch of results that require this one, so right?
Yes, but
You just did say recuse yourself from all of the Zorn-Sundberg type results.
yeah, if we follow the
I think I can't remember whether there's an effect also on sense.
Yeah, I don't remember that at the moment either. I know that there are some replacements for the null-Stellan thoughts constructively, but I don't remember the details. But it does remind me of the constructivist hymn that where there are no algorithms, we don't say anything.
I guess what was interesting to me is that it's not so much what they don't say, it's what they do say that's just completely counter to classical.
That's right.
And so if in algebra they just ignore all the horizontal required things, I'm like, okay, great. But if they say actively things that are just completely disagreement with classical mathematics, I'd like a collection of those things. List them on my wall.
Yeah, that's certainly a lot of fun. I mean, you can do this in basically any foundational basis, as long as you can develop recursion theory, which you can do basically anywhere. You can still have these results, which are valid as long as you restrict all their quantifiers to the recursive things, and maybe you have to throw in an application of Markov's rule if you want the really positively bizarre things. But even if you don't do that, you get the negatively bizarre things, so to speak. Okay, let's stop the recording for this time.